Okay, hi everybody. This is example 7.1 in chapter 7 on forces and or inclined planes and friction. And we may have done this example in class, but this is for the benefit of anybody who was not there for it. So we have a child on a toboggan, right, some sort of a sled type thing going down a hill. And so I'm going to go ahead and draw this. And for the time being, we're going to talk about an ice-covered hill. All right, and that's going, you know what? And I'm going to give myself a little more space right here. All right, talking about an ice-covered hill because we're not dealing with friction yet. So the hill it's slippery. It is virtually frictionless, we'll call it. All right, there's our hill right there. It is 20 degrees with respect to the horizontal. And here's our child on top of the, I'll draw him black right here. And there's our toboggan right there. And there's a child sitting on the toboggan, all right? Yay, there's our child. Okay, 20-meter long ice-covered hill. All right, we have the mass of the child, right? We have 10 kilograms, we're told right here, so it's not a very large child. Mass equals 10 kilograms. And there's no friction, and we have our angle right there. Okay. One thing I'm going to tell you is that I think there's part of what we're given here that is really not going to be very helpful at all, and that is 20 meters long. This right here is not going to come into play. In fact, I'm not even going to bother with it. I'm just telling you right now that is just extra information that we don't need. If we wanted to know about displacement and that kind of thing, then yeah, that would be beneficial, but that doesn't really do anything for us right now. So let's go ahead and start writing our forces in that we know exist. All right, first of all, we have the mass of the child times gravity, right? And that is always directed straight down, so we call that mg. But since we have the child on an inclined plane, we have the weight force, the mg. We have it really broken into two parts. Part of that weight force is directed straight into the hill. We call that the force perpendicular. And part of that weight force is directed downhill parallel to it, and we call that, of course, the force parallel. All right, force perpendicular, you probably recall, is mg. I'm not having much luck with, draw this over here. Force perpendicular is mg, still doesn't want to write, interesting. There we go. Cosine theta, and our force parallel is going to be mg sine theta. All right, and in fact, all that I should probably just have drawn over here anyway. How's that? There we go. That works because so it's all in there. Okay. We also have one other force that is acting on the child. All right, now it's not friction because it's an icy slope, but we do have the normal force. Right? The normal force is the force, you might call it the supporting force that the toboggan is applying to the child right here. All right, we call that N. All right, and N is always, and in fact normal literally means perpendicular. And so normal is going to be the same thing as the force perpendicular of the child's weight being directed into the hill, but it's going to be the hill's force that it applies back to support that weight. So the normal force and the force parallel, or sorry, force perpendicular, are almost always going to be the same thing. Okay, so let's go ahead with part A. Part A is, what is the acceleration of the child? All right, well, let's make a statement for our net force on the child here. All right, we can say that the net force is mass of the system, that is the child, mass of the child, times acceleration of the child as a system. Okay, it's also true. That's our kind of our system statement right there, but it's also true that the net force as components is the sum of all the forces that are acting to drive the child downhill. Now let's ask ourselves, is this force right here, is the weight force driving the child downhill? Well, no, not all of it. It's broken into two parts right here. Is the perpendicular force driving the child downhill, or is a normal force? No, they're acting perpendicular to the child's motion. So really the only force that is, or the only component force that is driving the child downhill is the force parallel. The force parallel and nothing else. Since it's a frictionless hill, there's not even any friction acting against it. So the net force and the only force acting on the child is force parallel, which is, of course, mg sine theta. Did I write that? Yes, okay. Okay, now why don't we just put them together, all right? mg sine theta is going to be equal to mass times acceleration. And if we're solving for acceleration, that should be easy. In fact, we can even cancel out the g's, right? Or I'm sorry, about the masses. That's the same. It's the mass of the child, which is the whole system. That's the mass of the child right there. So we can really say our acceleration is nothing more than g sine theta. What's g? Well, that's 9.81 meters per second squared, and theta is 20 degrees, so that should give us our acceleration for the child. And I want to say let's clear that, 9.81 sine 20 degrees, 3.36 meters per second squared. And that makes sense because it's not a very steep slope, and it's not like the child is free falling down the slope. Much of the child's weight force is directed into the hill, but about maybe a third of it is directed down the hill, which is what's accelerating the child down the hill. So that's part A right there. Part B is actually going to be even a little bit quicker, I believe, because all it's asking is what is the normal force exerted on the child by the toboggan. I've been saying the hill is supplying the normal force, but the hill is supporting the toboggan, and the toboggan is supporting the child. So really, if we look at our toboggan right here, all we care about is the fact that the toboggan itself is applying some sort of force on the child to keep the child up. Okay, so what is that force? Well, we actually kind of labeled it already before. The normal force is directed up, and why does it have to be directed up? Because there is a force perpendicular being directed down I'm saying the hill. It's being directed down into the toboggan. So what is a normal force? Well, it's going to be the same thing as the force perpendicular. Or we could say, if you want to really say this, the net force, let's make that black, sorry. The net force in the perpendicular direction is 0 newtons, right? Is the child moving up or down in the perpendicular to the hill direction? No, he isn't. Everything's balanced out. So we can say then that all those component forces in the perpendicular direction are, we'll call a normal force positive and force perpendicular negative. All right, if that's the case, then they're both equal to 0, and I think you can see easily that the normal force is going to be equal to the force parallel. Oh, sorry, force perpendicular, sorry. What's a more exact definition of the force perpendicular? That is mg cosine theta. So what's our normal force? Well, it's going to be what's the mass of our child? 10 kilograms times, oops, I'm going to run out of space, I know, 9.81 times the cosine of 20, barely got it in there. All right, so that's 10 times, so that's 98.1 cosine of 20 degrees. That should be pretty easy. 92.2 newtons, and that is our normal force. It's not the entire weight of the child because some of the child's weight is being directed downhill to move him, but it's most of the weight of the child. So there you have it. So we have our acceleration and we have our normal force. That's example 7.1. Please make sure you ask me if you have any questions, and I'll be glad to help you out. Thanks for watching. See you on the next one.